Hello and welcome back. In this video, we discuss about the principle of conservation of linear momentum applied to a fluid in motion. It is essentially the second law of Newton applied to a fluid system in motion. In the previous videos, we discussed about the concepts, system and control volume and a mathematical relation that connects systems dynamics to a control volume. By definition, a system refers to collection of matter of fixed mass, which may move, flow and interact with the surroundings. On the other hand, a control volume refers to a volume fixed in space through which fluid may flow. The volume is purely a geometrical entity and it is independent of mass. Reynolds' transport theorem is used to connect changes in system properties to its changes within and across a control volume. When system moves through a control volume, its extensive properties may change. For example, a change in momentum of a fluid system causes reactive forces on the control volume. In many engineering applications, we would rather be interested in this reactive force exerted on this control volume than the complex dynamics of the fluid system. Mathematically, we can show that rate of change of an extensive property, B, of a system, is equal to the rate of change of its intensive value integrated over the control volume plus its net flow over the control surface. This is called Reynolds' transport theorem. Although we have discussed this in previous videos, a review will improve your understanding on its application to the law of conservation of momentum. dB system by dt is rate of change of an extensive property of a system. For example, it can be rate of change of mass or momentum of the system. In the next term, small letter b is the intensive value of property B under consideration. Meaning of these terms can be discussed next. Raw dV is differential mass of system within the control volume. B raw dV is value of intensive property, for a differential mass of the system, within the control volume. Finally, the second term refers to the rate of change of value of intensive property, for a differential mass of the system within the control volume, integrated over the entire control volume. V.n is essentially the projected velocity of fluid particle to the normal vector of a differential area. This is velocity component normal to the differential area. Raw times V.n dA is mass flow rate through the area dA. Note that, if vector n and velocity v are orthogonal, no mass is crossing this area. Finally, when multiplying mass flow rate with intensive value of system property, and integrate over the entire surface, we see that the final term corresponds to net flow of intensive property into the control volume through the control surfaces. Now we can use Reynolds' transport theorem to derive an equation for conservation of linear momentum of a fluid system in motion. Let the extensive property, B, be linear momentum. That is, B system equals mv and its intensive value is small letter b, is v. Now, rate of change of linear momentum is force, which is described by Newton's second law of motion. Therefore dmv by dt will be sum of all forces acting on the system. The resulting equation is called linear momentum equation. The physical meaning is that the rate of change of linear momentum of system within the control volume, plus the net momentum flow across the control surface, will be equal to the net force acting on the fluid system. Consider the linear momentum equation again, derived using the Reynolds transport equation. Let us discuss the meaning of each term. Sigma F is sum of all forces acting on the system. The next term is the time rate of change of linear momentum of the system within the control volume. And the last term is the net flow rate of linear momentum through the control surface. The forces acting on the fluid system are, the body forces due to gravity, surface forces due to friction because of viscous effects, and pressure forces. In the next video, We will apply this momentum equation to a simple flow system such as a nozzle, and derive an expression for thrust developed. Thank you for listening.